Thank you everyone for attending this talk. Today I will be telling you about private aggregation of trajectories, and this is joint work with Badikasi, Newcomer, Ravi Kumar, and Anika Jang. In the trajectory aggregation problem, we are given multiple trajectories as input, and our algorithm would like to aggregate them into a single trajectory that well represents the input. As trajectories are some of the most basic spatio-temporal data, this problem has multiple applications. For example, each trajectory may represent users' travel path collected via GPS. Aggregating these paths can help us discover public transit routes or common travel paths. However, in such applications, trajectories can be sensitive as it contains user location data, and we want to make sure that our algorithm respects the user's privacy. The notion we use for privacy here is differential privacy. Roughly speaking, it says that adding or removing a single user shouldn't affect the algorithm output too much. Specifically, the output distribution of the algorithm shouldn't change too much. This is parameterized by two parameters, epsilon and delta. And for those who haven't seen differential privacy before, you should think of epsilon as being a small constant and delta being negligible in the number of trajectories. Throughout our work, we make several assumptions. For example, we assume that each trajectory is a polyline resulting from joining of the same number of points m. And furthermore, we assume that these trajectories are in sync in the sense that the j point of each trajectory correspond to the same section of the underlying trajectory. I will not go into more details or formalize these assumptions more, but in our full paper, we have a formalization of this under which we can prove some performance guarantee of our algorithms. A principal way to achieve differential privacy is to add noise to the output. And in our algorithm, we will also employ this strategy as well. Specifically, we will use as subroutine the so-called Gaussian mechanism. This is a very generic mechanism that applies to any function whose range is in R to the D. And it is very simple. Instead of outputting the function fx value directly, we output fx plus some noise c, which is drawn from the spherical Gaussian distribution scaled by a factor of sigma. Now, there is a question of how to set sigma such that we achieve epsilon delta differential privacy. Obviously, sigma will have to depend on epsilon and delta, but it also depends on another important parameter, which is the sensitivity of f. The sensitivity of f is defined as the maximum of the L2 norm of the difference between fx and fx prime, where x and x prime are ranging over all the input data sets that differ on a single user, or in our case, a single trajectory. It is known that we have to add noise that scale proportionally to the sensitivity to achieve epsilon delta dB. Now, let us get back from this generic Gaussian mechanism to our trajectory aggregation problem. Suppose we want to apply the Gaussian mechanism to our problem. What should we do? First, we have to select our function f. Now, there are multiple ways to define the function f for aggregating trajectory. In our paper, we use perhaps the most basic function, which is to average all the input trajectories point by point. Next, we have to answer what is the sensitivity of f so that we know how much noise to add. And in general, it is not obvious because different data set will result in different trajectory. But often the sensitivity can be inferred from the input domain. Specifically, if we know that the inputs are location data, then we know that each point in the trajectory is within a ball of radius r, where r is the radius of the Earth. This is illustrated below here. We call such a radius, such a bounding circle, a trivial bounding circle, which is the one that we can infer directly from the data format. Now, if we know that each point is within radius r of the origin, then since there are m points in each trajectory, we can compute the sensitivity of the averaging function to be r times square root m over n. And if we add noise according to this sensitivity and the formula from the previous slide, then we would get our differentially private trajectory aggregation. And this is indeed our first baseline, which we call the trivial bounding circle algorithm. Now, while this is okay, it's still not the best we can do. Specifically, the trivial bounding circle can be much larger than the area in which the trajectories actually reside. For example, in this case, if we were told this red circle, which contains all the input trajectory, then we would be able to add noise proportional to the radius of this circle, which can be much smaller than the trivial circle that we used earlier. Such a red circle will be called the global bounding circle. Unfortunately, the global bounding circle may not be possible to infer from the data format alone. And therefore, we have to look at the data themselves in order to find the global bounding circle. But since our data is sensitive, we have to do this privately. And the way we do it is as follows. First, we use the so-called sparse vector technique to compute the radius. And we will not go into the details here, but sparse vector technique is again a noising mechanism that is smart in the sense that it adds a little bit less noise than what we would have done trivially. Once we have the radius, we then divide the region into grid cells and compute the noisy histogram on the number of trajectories in each grid cell. Then we pick the grid cell with largest noise count, and then we let our global bounding circle be the smallest bounding circle containing the cell. So this gives us the global bounding circle, which we can then use to add less noise than the trivial bounding circle. And this is our second baseline. Again, this is an improvement over the previous baseline, but it turns out that it's not the best we can do. To see how we can improve it, let us zoom in into this global bounding circle. Recall that we average the trajectories point by point, which means that we start by averaging only these three first points. These points are in a bounding circle which is much smaller than the global bounding circle. This new bounding circle, we call it a local bounding circle. Again, if we know this local bounding circle, we can add noise proportional to its radius instead of the radius of the global bounding circle. So we will end up with much less noise. And this is the main underpinning idea of our final algorithm, which keeps this local bounding circle and advances it along the track as we build the aggregated track. More specifically, it works as follows. We start by finding the initial local bounding circle by running the previous algorithm for finding a global bounding circle, but instead of for all points in the trajectory, we only run it for the first 2 points in the trajectories. And then we repeat the following. We use the local bounding circle to compute the noisy aggregate of the current points. And then we move the local bounding circle center to this noisy average and then advance along as we construct our solution. So let's see this algorithm in action. Suppose that we have take the noisy average of the first 3 points, and this is our center for the local bounding box. Next, we want to average these 3 points. So we use this local bounding box and then we compute the noisy average. Suppose that this is the new noisy average. We then move the local bounding box to this noisy average. And then we compute the average of the next 3 points. And then we move this along. But now in this example, something interesting happened. The next 3 points that we want to aggregate are actually outside of the box. And this is something I have glossed over earlier, but this issue can be overcome by projecting these points onto the bounding circle and compute the noisy average. This ensures that the sensitivity is bounded as we want. And we continue doing this until we get all the noisy averages. And then we link them up to form our output trajectory. And that's it. That's our algorithm. We evaluate our algorithms on multiple datasets, including one containing migration route of pigeons, another containing strokes of characters, and another containing GPS bus routes. In all cases, our takeaway is that the global bounding circle indeed gives an improvement over the trivial bounding circle, and the local bounding circle also achieve a noticeable improvement over the global bounding circle. All right, let me end by mentioning two open questions. One is that since our algorithm is just averaging point by point, it's not very robust towards tracks that have different lengths or are not in sync. It would be nice to have an algorithm that is more robust towards these issues. Another is that there are non-private algorithms with theoretical guarantees for certain objective functions. It would be nice to make them work in the private setting as well. And with that, thank you all very much for your attention. Thank you.